to my science experiment, and let's look at the application of the thermal emission spectrometer spectral data to terrestrial desert varnished rocks. My name is Taylor Fireisel, and I'm a student here at Arizona State University. Thanks to NASA spacecraft around the world, this whole project was able to happen. Let's get into it. So on Mars, Mars has a history of thermal infrared remote sensing, and recently, in the last decade or so, they've launched two orbiters. One is the Mars Global Surveyor, and another is Mars Odyssey 2001. Mars Global Surveyor went into safe mode less than 2 years ago, but on it was the thermal emission spectrometer, which we use to get the surface type 1 and surface type 2 spectra data. Also, on the Mars Odyssey, there's a DEMIS camera, which is the thermal emission imaging system, which uses thermal infrared to detect what type of rocks are on the surface. From the test, they have the two surface type 1 and surface type 2, and in the red pixels the surface type 2, and in the green pixels the surface type 1. Both these have characterized the spectra for surface type 2 and surface type 1. And so what we're trying to figure out is the surface type 2 rock surfaces on Mars. And to figure that out, I hypothesized that it is a rock coating on the rock surfaces that is manipulating this different spectra of the surface type 2 rocks on Mars. This coating is a desert varnish, and what we're going to do is we're going to get 34 rock samples from around the world in arid environments and take spectral analysis of these rock varnishes and try to see if there's a correlation between this spectra of surface type 2 and the spectra of the 34 rock desert varnishes. So this is the spectrometer lab, where I used a laboratory spectroscopy to analyze the rocks. And the rocks that we used were varnish coating rocks that we got from around the world in arid environments. The arid environments specifically were the deserts in the southwest United States, Argentina, and India. And here's some examples of the rocks right here. You can see that there's a little coating on top. It's a little different than the fresh layer. The fresh is the interior, and the exterior is the varnish. And what we do is we heat these rocks up to 80 degrees Celsius in the oven. And this is the oven. And right here is two rocks that we use specifically. This is rock 30, this is rock 16. And so when we heat them up, once they're nice and hot, we're making sure that they're all at the same temperature so it's calibrated correctly with the black bodies that we compare it to find out the emissivity. And so we take the rocks from the oven and we put in the spectrometer. Now this is a Nicolette Nexus 670 spectrometer. And you open this, you can see that there's already a rock in there. And you put the rock on a styrofoam pad, or if it's a really big rock, you don't need a styrofoam pad, you just lift it up. And then you raise the rock up into the can. And that copper cylinder is the can. And once it gets up there, so you rise it up, and it's ready to be analyzed. And for spectral analysis, we use the program Omnic, which calculates the emittance of the rock per wave number, which is the reciprocal of wavelength, so it actually calculates the radiance at each wavelength of which the rock's emitting. And as you can see, the spectra are different. It characterizes the rock, and it's an absorption spectra. And here's the plot of which Da Vinci calculates, and we use these plots for our results and compare it to the surface type 2 emissivity plot. And we also use the spectral analysis tool to compare this spectra to a well-characterized spectral library at the Mars Space Flight Facility to find out actually what type of clay minerals are in the clay varnish. And let's go back to the classroom to show you the results. Alright, so now we're back in the classroom, and utilizing the emissivity graphs that we made using Da Vinci, we came up with some results. The results were that fresh surfaces were primarily basalt and obsidian. As you can see in the green spectra is basalt and the blue spectra is obsidian. Now both these rock samples had varnished layers, and after doing using laboratory spectroscopy on them, we figured out that the varnish was very similar and that the desert varnishes were the same on various fresh surfaces. Now getting into the meat of what we were hypothesizing was now we're going to analyze the typical varnish. So after taking 34 samples and taking multiple spectras of the varnish on those samples, we found out a typical varnish. And when I say typical varnish, I mean it was the most abundant. And this typical varnish was unknown. We don't know what this varnish is. And so what we did was we compared this varnish spectra to a well-characterized spectral lab at the Mars Space Flight Facility, and we found out that the clay mineral montmorillonite was the most closely related to the desert varnish. Also, you can see that the montmorillonite is not 100% exact for the typical varnish, so what we use is a spectral analysis tool to find the best model fit by taking different percentages of different clays and putting it together to find the best model fit for the varnish. And what we found is in the blue spectra is the best model fit. And that's a lot closer than the pure montmorillonite. And so the best model fit consisted of 39% montmorillonite, 26% sodium-rich montmorillonite, and 34% of other clays. And you can see that's a lot more closer than pure montmorillonite. So varnishes vary considerably within the individual varnish itself. So after looking at the results, we can conclude that the desert varnish does not completely characterize the surface type 2 rock surfaces on Mars. But we found out that the varnish consisted mostly of montmorillonite. Also, desert varnishes uses the surrounding environment as a means of classification and transportation to come up with materials to create this varnish. For future work, we noticed that the varnish, we compared the varnish spectra to a bunch of calcium, sodium, and iron-rich clays, but we didn't compare it to manganese-rich clays. So in the future, what we're going to try to find out is the emissivity plot of manganese and try to compare it to surface type 2. And maybe that will be a correlation because desert varnishes are also manganese-rich. So it might be a manganese-rich varnish rather than a calcium-rich varnish or a montmorillonite-rich varnish. Thank you for watching my science experiment, and